1.
So, good morning, Anuna. So, my topic is round robin. Myself, Chandana. So, these are the contents. Um, Title page, introduction, overview of round robin scheduling, experimental setup, implementation steps, flowchart, Python code, program output, observation, comparative evaluation, analysis, and conclusion. So, the first introduction, operating system scheduling. Operating system scheduling is the process of deciding the order in which processes are given access to the CPU. Since the multiple processes may be ready to execute at the same time, the scheduler ensures fair CPU sharing, efficient resource utilization, and minimizing waiting time. An efficient scheduling algorithm improves system responsiveness, throughput, and overall performance, especially in multitasking environments. So next, overview of the round robin scheduling. Algorithm round robin is primitive CPU schedule algorithm designed primarily for time sharing systems. Each process is assigned a fixed time quantum, also known as time slice. A process can execute only for one quantum at a time. If it does not finish within that interval, it is permitted and placed at the end of the ready queue. So next, objectives. The main objectives of the assignments are to design and implement a round robin scheduling algorithm with configurable time quantum, to experiment with at least four different quantum sizes using the same set of processes, to measure and key performance metrics such as waiting time, time around time, turnaround time, number of context switches, CPU efficiency by selecting the most balanced quantum value. So next, to analyze how quantum size affects performance and justify the optimal quantum for the given process set, to optimize system responsiveness and effective efficiency by selecting the most balanced quantum value. Next, the experimental setup, programming language and tools. For this equipment, the round robin scheduling algorithm was implemented using the Python programming language due to its simplicity, readability, and suitability for quick simulations and analysis. The following tools were used: IDE editor, Visual Studio Code, Python version, Python 3x, and then optional tools are Jupyter Notebook for running si- simulations and visualizing results, online Python interpreter. Next, experimental setup, uh, a custom dataset of dataset description. Processes was prepared to test the round robin scheduling algorithm. Each process will Each process includes attributes such as process ID, arrival time, and burst time. And if you this is standard value dataset. These are the values which we have taken. This dataset was chosen because the arrival times are staggered, representing a realistic environment. Burst time vary, allowing for meaningful comparison of performance across different quantum values. Next, time quantum values are tested to evaluate the effect of quantum size on system performance. Four different quantum values were tested using the same process set. These quantum sizes covers. So we have taken the quantum value. So small quantum 2 ms high context switching, quantum 4 to 6 ms balanced performance, large quantum 8 ms FC first come first serve like behavior. So next, implementation step. Step by step procedure. Start the program, input the number of processes, input the time quantum selected for the experiment, initialize required data structure, sort process by arrival time to simulate real CPU scheduling conditions. Begin round robin execution loop. Repeat the loop until all processes complete. Calculate waiting time and turnaround time for all processes, and then next generate the Gantt chart based on execution order and time intervals. Next, display output, then stop the program. So this is the flowchart. Start, then input processes and time quantum, then initialize ready queue and remaining times, then any processor arrive. If no, then get tires ready queue. If yes, execute processes for minimum, then remaining, then record completion time. If no, then all processes completed. So next, this is the code. This Python program implements the round robin CPU scheduling algorithm. It takes list of processes, burst time, arrival time, time quantum, and returns waiting time for each process, turnaround time. Then this is the remaining code. Then this is the output of this program, Python program. Then the comparative evaluation to understand how the time quantum affects the performance of the round robin scheduling algorithm for four quantum values 2ms, 4ms, 6ms, and 8ms were tested on the same dataset of processors. The following performance metrics was compared: average waiting time, average turnaround time, number of contact switches, and then the comparison time quantum are like this. This is the table. Then the comparison table, then explanation of this comparison. Waiting time decreases steadily as the quantum increases. Quantum is equals to 2ms produced the highest waiting time because processes were preempted very frequently. Then quantum number 8ms bad had the best waiting time but acted more like a first come first serve, uses less, it is less fair for short takes. Then next, turnaround time. A larger quantum resulted in lower turnaround time. Quantum 4ms and quantum 6ms provided a good balance between fairness and performance. Very small quantum increased the turnaround time due to excessive context switching. Next, context switch. The number of context switches was highest at quantum 2ms for 17 switches. Then, context switching reduced CPU efficiency, so lower is better. Quantum 8ms had the fewest switches but loses the advantage of true timing sharing. And then, next, the conclusion of this comparative study. Among the four tested quantum values, 6ms provide the best balance between low waiting time, low turnaround time, reduced contact switching, good interactivity. Thus, the 6ms can be considered the optimal quantum for the given dataset. Then this is the comparison table for first the P1 to P4. Too many contact switches, inefficient but highly responsive. Then next quantum 4, balanced performance, good for general use. Then quantum 6, best overall balance, low delays and fewer. Then 8, lowest overhead, behave close to first come first serve. Then the short analysis of this comparison table is: from the comparison table it is clearer that quantum size directly affects system performance. Small quantum 2ms results in high contact switching, increasing overhead and waiting time. Medium quantum provide the best balance between responsiveness and efficiency. 6ms performs the best overall, the lower working time and fewer switches. So next, the larger quantum minimize contact switching but reduce fairness and begins to behave like a non-primitive algorithm. Therefore, 6ms is the optimal quantum for this dataset, offering efficiency CPU usage, relatively lower turnaround time, and fair process distribution. Then the conclusion for this, the experiment shows that the performance of the round robin scheduling depends heavily on the time quantum. Small quantums increase contrast switching, while large quantums reduce fairness among four tested values. The 6ms quantum gave the best balance with lower waiting time, low turnaround time, and fewer contact switches. Therefore, 6ms is the best efficient quantum balance for this dataset. Thank you all.